Hi class, welcome to my jet performance presentation. I tried to do something kind of fun with the presentation and I didn't pick an aircraft that has already been designed. So we'll see if what you guys think of this. I took for my aircraft, I am using the aircraft that my group is using for our ARAPA project. And as we all know, that has to be a propeller driven aircraft. I decided to pick, our group decided to pick the PC-12. So what I did is I took the ARAPA data that we have for this in the drag module, and I used it for this module. And since this module we had to pick a jet aircraft, I decided to mate the Williams FJ33-5A engine, which is basically used on VLJ aircraft, and mated it with the PC-12 just to get an idea with the PC-12 drag profile, what kind of speeds I would get with this aircraft. So I'm looking at the maximum forward speed and level flight. I chose the maximum endurance airspeed, and I chose the maximum range airspeed. So the way the presentation is going to work, I'll look at both our drag chart and the drag table and kind of walk you through how I found these three items using both tools. So first things first, let's look at a few assumptions before we get into the data. As we all know, the data that is put out by Williams is from the marketing department more than likely. So the power plant assumptions is basically the sea level, pressure, altitude on a standard day, 0% humidity, no accessory gearbox loads, no bleed air extraction, and 0% inlet total pressure loss, and then your exhaust as applicable with the engine installation manual. So if you look at all the bullet points, it's basically to get the most performance out of the engine that is possible. So when we go to calculate the thrust available from the engine, I obviously don't have some of the data needed for the formula to calculate. However, thrust available equals the mass airflow, which is typically in slugs per second, and then you take your exit velocity and subtract your inlet velocity and multiply that by the mass airflow, and you come up with a poundage for thrust on the engine. I don't have that data, so luckily Williams does give us that data. And I can tell you that the engine from the type data certificate from EASA shows that it has 1846 pounds of thrust under the assumptions above. So we're going to use that number, and then we're going to throw that in together with the drag data that we have for the PC-12, and we'll see what we come up with. So let's look first at the maximum forward speed in level flight. That's one of the selections that I chose. I thought it'd be interesting to see what this aircraft can do with a jet engine on it, assuming that the drag profile stays the same. Drag chart from our aircraft. The blue line is the total drag chart, or total drag line, which is what we're interested in here. And basically we know that thrust directly opposes drag. So in reality, this drag chart, we can also use it as a thrust required chart to offset the drag to find the speed, the maximum forward speed that we need. So again, let's take our data. We do know that the FJ33-5A produces 1846 pounds of thrust. So what we're going to do is on the left hand, the Y column, the left hand side there, I have pounds listed. So we're going to enter the chart at the 1846 pounds of thrust, and we're going to take that over to the total drag line, and we're going to run that down, and we're going to see what the speed is. So this is showing about 267 knots. It would be the speed that we could maintain in level flight with the thrust that's available from this engine. So let's take that data and let's just kind of double check ourselves using the drag table, and we'll see where we fall. All right, so here's the drag table that my group came up with for the ARAPA project for the PC-12. And keep in mind, this is the drag table with the turboprop engine on it. So we're going to use the same numbers that the aircraft has with that engine, and we're going to compare it with the jet engine here, assuming that nothing changes as far as the drag goes. So we know from our table that we were looking, or our chart that we were looking at 267 knots, which falls in between the 251 and the 271. And if you come over to the right-hand side, the total drag is in between 1885.94 and 1630.9. So we know that our numbers fall within this range. So what we need to do is go back to, I believe it was module 1, and interpolate the data in between these two rows. So in order to do that, we take the 1885.94, subtract the 1630.9, and we come up with 254.04 pounds. And then likewise, if we do that same calculation on the left side, we know that that 254 pounds, or 255.04 pounds, is over the span of 20 knots. So we need to break that down and find out how many pounds per knot it's changing. Now, I know it's not, our drag curve is not completely, truly linear. It's a curve, but we're looking at such a short span here, I thought it would be appropriate to kind of get us in the ballpark and see where we're at, just to double check the chart that we looked at earlier. So again, if we take the 255.04 and divide that by the 20 knots, we're basically close to 13 knots, 13 pounds per knot, 12.752. So now we can take that data and we can subtract the 271 minus 267, which is what we came up with on the table in the previous slide. And that comes up to about 4 knots, and then we multiply that out, and we come up with about 51 pounds of difference there. And if we take that, since the 267 is closest to 271 knots, we subtract the 51 pounds from the 1885.94, and we come up with 1834.93. So we know that the engine, the FJ33 engine, has more thrust than that. So we should be able to, in theory, maintain that 267 knots. And if we go 1 knot beyond what we're capable of, we shouldn't be able to maintain the 268. So let's check that, and you can see the mathematical formulas and the steps that I use there on the right-hand side to calculate that. And it does check. 1847.68 pounds of drag, which is more than what the engine is capable of doing. So we should be pretty close to the 267 knots as the max forward speed in level flight. So next up, let's look at the maximum endurance airspeed. Okay, so again, we're going to go back to the drag table to calculate the maximum endurance airspeed. And if you look in the book, they describe the maximum endurance airspeed as LD max. So we've already calculated this for the PC-12 during the last module. So we need to come in at the coefficient of lift over the coefficient of drag column and find the biggest number there. So we have 15.5008, which, if you run that to the left, is connected with the 111 knots. So this one's pretty easy. The LD max for the airplane is 111, and that gives us our maximum endurance. Now let's double check that with the drag chart and see if we come up with something close there. So looking at the LD max here, we come in at the 111 knots at the on the X axis, and we come up until we hit the total drag line, and then run that to the left for pounds, and it looks like about 583.96 pounds. And looking back at the drag chart, that is the total drag, that far right hand column. So our number should be pretty accurate for the maximum endurance airspeed. Okay, up next is the final airspeed here. We're going to try to calculate the maximum range airspeed for the aircraft. And this is going to be a little bit different than the maximum endurance and a little bit more involved here. First off, let's look at a couple of assumptions. I was able to find some fuel burn data on the Williams engine here, and it looks like 0.49 pounds fuel burn per 1 pound of thrust per hour is what I came up with from my reference there. And the two other assumptions that go along with it, the test was done at sea level, or the number is from sea level and a static engine. In other words, it was on a test stand when they ran the test. So in actual use, the fuel burns are probably going to be a little bit higher. But this is the only data I was able to find, so we're going to go ahead and run with it here. So looking at the drag table once again, we're going to use this to calculate the specific range max, which occurs at fuel flow divided by velocity, and we're looking for the minimum value there. So in order to do that with our drag table, we're going to need to calculate each row to see which one has the lowest ratio. And let's just start with the 71 knot column. So the total drag here is 794.22, and we know that to offset that drag total, we need thrust required, which is going to equate to 794.22 pounds of thrust. So with that in mind, we're going to multiply that by the fuel burn rate for each pound of thrust, and we come up with a figure of 389.17 pounds per hour. So once we know the fuel burn, then we can take the fuel burn, divide that by the 71 knots, the true airspeed, and we come up with a figure of 5.48. And we're just going to go ahead and plot that to the right of the table there. And we're going to apply this technique for the rest of the rows on the table, and we're going to find out which factor is the lowest here. I did not calculate the last two rows. I did not calculate 291 or 311 knot true airspeed rows, because we know from our earlier calculations that the maximum forward airspeed in steady flight is below that. We know it was 267, so I did the 271 knot row just to cover our bases, to make sure we included the 267 knots. And all we're looking for here is the lowest value, and it looks like 2.33 is the lowest value there. And if you run that over to the left, it looks like 151 knots, based on the speeds that we have selected, would be or give us our maximum range airspeed. Now let's take that and we'll run it through the drag chart, and we should come up with roughly the same number. So this calculation is a little more difficult. We're trying to find the lowest angle from the point of origin, starting at the point of origin up to the green curve there, which is my fuel burn curve. So taking those fuel burn numbers from the table that we looked at in the previous slide, I was able to plot that. So that's our fuel burn per hour there for each airspeed located on the X-axis. and I plotted that on the chart. So we're just going to take a line from the point of origin, and we're basically going to look for the smallest angle between that red line and the x-axis. And we're just going to take where it intersects the green line there and run that down. And as you can see, it makes a right triangle. So the angle at the origin there would be the tangent min is what we're looking for. So that should be the minimum angle, which looks like about 151 knots based on the labels there on the x-axis. It should give us our minimum value. If we were to take that red line and intersect anywhere else on the green curve, that tangent angle would be greater. So 151 knots should be about the maximum range airspeed for this aircraft mounted with the Williams FJ33 engine, which was kind of interesting. Just to cover our bases, the references I used, Garrison was from the Flying Magazine article I found online, and that gave us the 0.49 pounds fuel burn per pound of thrust per hour. That was the only fuel burn numbers I could really find for the engine, so we just went ahead and used that. And then the type certificate data sheet that was published by EASA for the FJ4433 series engines gave us our total maximum thrust that the engine would produce. And again, if you remember our assumptions from earlier, that was basically an engine on the test stand there with no accessory gearbox or extracting any bleed air off of it standard day. So it was the best that that engine could do possible. In all applications, that number, the total thrust is going to be lower just because you're using some of that energy to run accessories, fuel pumps, hydraulic pumps, and you're going to extract bleed air off the engine as well for pressurization and other pneumatic things. So it was the best we had. I really enjoyed the putting the two together, the airframe and the engine, to see what it came up with. I hope you guys enjoyed it, and I look forward to discussions on it. Thanks for watching.